Okay, how do I look smarter? Hello, world. My name is Alan. We're practicing LeetCode. And as part of interview preparation. And today we will see what we can do with this problem. Combination sum 3. Well, 3 sounds a bit scary. I don't remember the combination sum 1 or 2 or so, but let's see. Let's see what we can do. Let's see if we can do this within I don't know, let's say 30 minutes. So find all valid combinations of k numbers. K is from 2 to 9. Okay, so the screen is reflecting that window a little bit, so find all valid combinations of k numbers that sum up to n. Well, such that the following conditions are true. Only numbers 1 through 9 are used. Each number is used at most once. We'll return a list of all possible valid combinations. The list must not contain the same combination twice. The combinations may be returned in any order. All possible valid. Okay, so let's look at the examples because I don't think I got it. Okay, we have K3. Combination of K3 numbers that sum up to N7. Okay, in output 1, 2, and 4. 3 numbers. Explanation 1, 2, and 4. They sum up to 7. There are no other valid combinations. Well, you need, okay, I understand what it means to sum up. So understand that you need 3 numbers. So exactly 3. And they need to sum up to 7. And, each number is used most once. Okay, so that means, like in this example, you can't take like 2 and 2 and 3 because there is a repeating 2. So, and it has to be smaller than 7, right? But it has to be at least, I don't know why it says K is at least 2, while at the same time only numbers 1 through 9 are used. Maybe it's, yeah, there's a typo here. Rarely I see typos in LeetCode, but that could be the one. If I understand it correctly, if I'm not misreading it. Yeah, so you can't use 0. So yeah, so to get the 7, you can use 7, but then you cannot, you need 2 more numbers. So you can use, let's say, if we use 4, if we use 5, we have two more to add, and that is like 1 and 1 or 2 and 0. So no, we don't have, which we can't do. So here we start with like 3. Then we need to get 4 as a sum. So that's 1 over 3. It's 2 and 2. So we can't get that. Yeah, so this, it's essentially a tree. We'll be building a tree from which will start with 3. Then we'll use any of other numbers left. And if the sum is, if it sums up to that, yeah, so how about that? And so the sum could be bigger. Some could be up to 60. Yeah, let's check out other examples. 9. Okay, now 3 numbers. Okay, 3. I see now what. Okay, k is not that range. K is the number of these numbers. So there are at least 2 numbers. So it's not a typo. There is at least 2 numbers, but maximum 9. Okay. So in that, the tree. Yeah, so we'll have, let's say in the second example, we have 3 numbers. So there'll be 1, 2, 3. And, but the sum needs to be 9. So it's going to be, yeah, we're going to take from 1, 2, 3, not 9. 1, 2, so that 3, that's 6. Then we're gonna have 1. That's it. You can't get any other ways. 1, 3. If it's 3, then it's 5. And 1, 4. If it's 1, 4. Well, this already is 5, and we need 4 here, so that we can't do that. There is no 1, 4, that's 5. We need 4, so we don't have 4 anymore. So 1. Yeah, so then we'll use 1, and we are not gonna be going. Well, essentially, it's if the remainder is smaller. Yeah, it looks like we can go only with a growing number. Yeah, because if we go, we don't need to check the smaller numbers. Yeah. So if the remainder is smaller, we don't go, as long as the remainder is bigger. So starting with 4, the remainder is not bigger, but we need to go for something bigger. Yeah, so that's why we'll go to 2, and that gives us 2 gives us 3. 2, that's 5. And wait a second. Yeah, so the remainder is bigger. Yeah, 4. Is bigger than the current number. That's what we're comparing with. Yeah, and then the last number. Okay. Yeah, so it looks like, yeah, once we get the sum, it looks like backtracking. We're gonna just try them all. What's the time complexity? If there is like 9 numbers, for each number, it's essentially 10 to the power of 9. Max. Well, 9 to the power of 9, so. So we need to, yeah, if we don't have to track visited. If we just go to the, if we pass a slice of these numbers, the remainder, yeah, we will be looking at just the bigger ones, those that are bigger. So we can create initially our nums is a slice of integers, which will have 1, 5, 6, 7, 8, 9. Eight, nine. So, we can try depth first search, right? To build these trees. So we'll have variable dfs will be type function. It's gonna take at least a slice of numbers. Yeah, nums of type slice of integers. You can also take some integer because we need to track it had sum and check. And we can only go this number of time. The max number is n. The k is 9. Yeah. So essentially, we need to. Well, if we do, I mean, we can do it we can call it iteratively, because we know the number of times we need to go. We can should we do recursion or recursive solution or iterative solution? I'm thinking, let's try. I mean, if we do recursive, we need to track this length. Because we only want to go this number of times, times. Yeah, so length, or this is what k is. Or we can do just iteration up to for a range k and nh. iteration. The thing is, we need to get like to generate the first number. Yeah, like the first number will be generated 9 times. By the way, we don't need to go to the 9. We only need to go to the n. So nums we should, because yeah, when n is 7, yeah, we don't need to go more than 7. Yeah, so to initialize this nums, we should do it for I is 1, I less equals n. And yeah, I mean, essentially, if there's like k numbers, so there is at least essentially n is not the maximum one. The maximum would be at best n minus k. So if it's like 3 numbers you need to generate, so you need to at least 2 more. Yeah. N minus k, by the way, in this situation, it's minus 3. Yeah, so when you need to return the, essentially, and we need to return the slice of slices. I need to return of all possible valid combinations. So the answer is going to be slice of slices of integers. Yeah, but this nums. Yeah, because I think it's minus k, because you see it's minus 3, not, why is it not minus 2? Because every number, yeah, if it's like, if it was 1, if the length was 2, it would be, the length was 2. K was 2. Which means that number minus 1. So 6 and 1. Wait a second. N is 7. There is never the n itself, unless it's only one number. The n, but there is never just one number. So then anyways, yeah, if it's one number, there will be n, minus k. So if there's two numbers, it will be n, which is 7, minus 2. So we'll get 5 at best. But we need 6 and 1 as a combination. I don't think it's that important. I think we could even do the and. Could even do the and. The algorithm will take care of it later. But I mean, yeah, because we can't do, if case 2, yeah, you need an n is 7 and minus. You'll get 5 at best, but you need 6, right? So it's like plus 1. Or I would just say go with n. If we say plus 1, that will work like, in this case, it will be n minus 2, which will be 5, up to 5, which is no, that's the case for that one. So for that one, 9 minus 3, which is 6. And that, I think, works. Yeah, in this case, 7 minus 3, which is 4, works. 7 minus, yeah, when there's 2, it's not going to work. 2 numbers. To get the sum of 7, 2 numbers, yeah. So I think we can even, yeah, so it's different. So we can just do like, let's do n. And we might have been just fine with the full length. So, anyways, yeah, so 22 minutes. Yeah, I think we pretty much get the logic overall. Yeah, DFS with these numbers. Yeah, for simplicity, we can just even do that. And if you want to, we can say like nums is nums till n, not including n. Okay, so we're never gonna get the n itself. If you want to, we can even do it like that. Yeah. But what else? Then, yeah, we'll generate those numbers starting. We'll pass that slice. And to the function, that function will go over these numbers starting with this one in the ascending order, and create a node. And then there will be yeah, but can you do then you'll need one more call. So this number of calls, you just stop at when it's not giving you the sum. It feels like recursive is a little bit more familiar for me in that case. We do need to track the depth. Yeah. Because the depth is going to be initially 1. And yeah, we'll have the call. So sum is that. The depth, which is that's actually how many numbers we have in that combination. So that's essentially the size of this combination. Well, typically you call the size as yeah, so when you call it first, the current size of the combination is 0. If that's, yeah, then we'll call it with nums. We'll pass then so now we're looking, we have it in the first call, we have the full list. Okay. And we're going to go over them, but we need to check if sum, it needs to be small. Well, the size needs to be smaller than because if size is, the exit case, the base case is, the good case is size is equals k, and sum equals n. In that case, we need to slices clone, create a copy of the slice, which will be, by the way, we need to track that combination. Comb. And by the way, we don't, if we have a nested, we don't need to do that. We can keep them all outside. We just need to we can keep them all outside if we don't keep the It's kind of easier when you have those within the call, kind of easier. But why don't we also then pass the combination into the call? Yeah, so the combination is a combination, also slice of bytes. Yeah, so that combination is going to be just an empty slice of bytes. Not bytes, integers. And what is this thing doing here? Well, this thing is going to go over, do something here, yeah. So if we are at the point, yeah, the size is k, is n. Yeah, we'll clone that comb. And we append it. We say the answer, append answer, and then this, yeah, this cloned. Yeah, we reached 30 minutes, by the way. Okay, that's the base case. Additional 10 minutes. What if we... Yeah, I mean... in each call, and by the way, the first call size should not be 0. Well, sum and size, they both are 0 initially. So maybe they should, yeah. But then they are different. Yeah, we update them. So we only need to do that if k is smaller. If k, if size, current size is less than k. Yeah. If it's bigger, we can just say like return. Because we don't need to do anything. So by the way, we need to return here as well. Yeah. And once we reach it, yeah, we'll come to this number of digits. Yeah, we'll pass it, and we come. And by the way, do we really need to track size as it is? We have the comp length, so we don't really need to track that. We'll be increasing comp, so the sum, yeah, we want to track, but yes, so not size, but length of comp. Yeah, but what if the length of comp is bigger than k? Oh, we just don't need to do anything, yeah, basically. Yeah, only if it's smaller. Turn. We can do it like that as well, yeah. So if there was a case, okay, the sum. So we reached k, but sum was not right. So then we got to the next k, and k become bigger. Well, it looks a bit awkward, but anyways, yeah, it kind of makes sense. So now, okay, we can generate the number. Not like that. So we need to go over the nums and try to get the first number into our combination. Yeah. That will give us the first number, 1. And we're going to call DFS. But now we're going to call DFS without that. Yeah, we're going to call nums, but we're going to cut. I'm going to start with 1 plus with I plus 1 and the rest. When that number so that combination where do we get the number? Okay, so should we just take the first number in that? No, it's not like Q. Yes, this is where we get the first number. We say that append combination and the, right? Because we want to try these. You want to try all of them, except maybe those that are above. But yeah, so we get the number. That's the number, and we need to pass their sum. Now we need to pass that sum plus v. So that next call get only the bigger ones with our combination now has one number, this added, that number added. And the sum is there. If we check if we have the match, we append it. If we don't, we try to add a bigger number and try to add a bigger number to it. If sum is bigger than the sum, yeah, we don't have to, we return. Essentially, we need to do that call only. Yeah, well, or sum is bigger than m. That's probably it. Oh, we need to say like integer, yeah. Oh. Yay! Error. Runtime error. Slice out of bound. No. With capacity 9. Oh, I think I got it. Oh, we wanted to limit it, but we don't need to. Yes, so there are ways to nice to like for optimism. There is room for optimization. But, essentially, that's the way to go. I like how simple it is. Look at that. Look at that. Look at that. That's a pretty simple. Yeah, nice and short. That's nice and short. Lovely. So 40 minutes, around 40 minutes to solve it. Using DFS, backtracking. Yeah, we might refactor these. I mean, we can move this if here, but and do that call only. But it's good to have it separate. Like, okay, if we ran out of the length, stop. Okay, just you're done. Yeah, with that. Yeah, that's out of the length or out of sum. So when these attempts, which is what backtracking is, you do that. You do an attempt, try it, and if that doesn't work, you go back. Yeah, you'll try another one. When we try those, we'll stop at once we hit these limits. I mean, this is essentially, these are like essentially the leaves of that tree. We're gonna try decision tree. Yeah, we're gonna try. Okay, this number. Now, yeah, if I mean, we could obviously when the combination length is already k, you return anyway. So yeah, we could refactor it in some ways. Like we could say if we have k, we round. But then depends on what sum is. Yeah, so yeah, we can do it a little bit, refactor this a little bit different. Like let's say if we have k, and but then we need to check what's the, if sum is n, then we append it. But if sum is and we don't even have to call it. Yeah, we can check it even here without these. If sum is n, yes. I mean, we can do all those you see here. If sum, so we are going, whatever. Okay, so here is the deal. We might not have reached the k, but once if sum is bigger, we need to return. So so it's sort of a little bit it looks a bit more simple when you have those checks like that. Like we know that's when we need to append and we need to return, and then that's it. Yeah, and that also, yeah, so I like that. Anyways, that's medium level problem solved within 45 minutes, let's put it that way. Good practice. Next target would be probably to do it within 30. Yeah, we're trying to do it within 30 minutes, so working on it. Thank you for watching. If you like these videos, like and subscribe, and we'll see you in the next video.